The wave-particle duality of the electron means that the electron can be treated as a Newtonian object, or it can be treated as a wave function object. Wave particle can be one or the other. Until the modern times, the electron was essentially considered a spherical mass orbiting the nucleus of the atom and had Newtonian properties and was treated in that same context. However, along came in the due time the following experiment. This is a cathode ray tube which had a collector and a source of electrons, and it generated an electron beam. This was connected to a strong transformer. You saw one example in the radiation discharge tube of hydrogen when I showed it to you a few weeks ago. But between these electrodes, this one would be negative, this one would be positive side, is one would observe a stream, which is green in nature, of electrons. It was, and when tested with, let's say, magnets, a positive end versus the negative end, of course there was attraction and repulsion of the electrons, because this was an electron beam with a negative charge character to it. So they knew what it was, and so the idea was, here's a bunch of particles running between electrodes. Well, some bright guy comes up and puts a prism in there, or a diffraction grating. Just took me a second to get the cobwebs out. And all of a sudden they observed, as the electrons passed through that, a spectrum. Like the bright line spectrum, except this was an electron spectrum. It produced lines, emission lines, on a screen that was mounted inside the cathode ray tube. Well, the point is of showing you this is, until that was done, until the cathode ray tube experiment was done, electrons were considered to be Newtonian in nature. However, when they only light at that point showed a diffraction patterns. So as I'm trying to shorten up the million of years of evolution of this thing, because only light originally showed diffraction patterns, the nature of the electron, once it demonstrated a diffraction pattern, could now be considered or analyzed having a wave behavior. And when we go into wave behavior analysis, it is defined only in terms of probability and statistics. Wave behavior is statistical analysis at best, and depends upon probability. Analysis. So, in the postulates now of the Schrodinger model, and I send you to online to make you a printout of this, but we'll look at it here also, save me time and use time of writing all this down. Oops, a little bit, maybe too far. We'll back it out just a tad. Not attach enough. Come on. There we go. Oh. Okay. Hopefully you can read that. Well, I thought I could get it a little bigger than that. That's better. Okay, just simply put, now what it says, experimental postulates. Electrons have a wave-particle duality. That is, they demonstrate both wave and particle characteristics as defined by what we call a de Broglie relationship. A guy named de Broglie came up with this equation, which is impossible to see. Actually, it should be lowercase h because that's Planck's constant. And m times c. This is the de Broglie relationship. The de Broglie relationship relates wavelength to the movements of matter. That should be a v, but we put the speed of light in there. But this is a velocity right there. All matter in motion generates wavelengths. One of the issues, like you walking down the street, generates a wave that's so long it can't be detected. However, when you get on the subnuclear level with something moving in the vicinity of the speed of light, it will have a specific wavelength. So that postulate says that there is a wave-particle duality. The de Broglie equation defines wave-particle duality. You need to write that down 100 times. De Broglie, D-E-B-R-O-G-L-I-E relation, right here, de Broglie relation defines wave-particle duality. And learn the equation. You might have a problem where I'm asking you to give you a velocity 99% speed of light. What's the wavelength? And this is the equation you would use. A second postulate, both position and momentum of the electron about the nucleus cannot be defined with certainty as defined by what is called Heisenberg uncertainty principle, a very classic principle in the world of atomic physics is the Heisenberg uncertainty principle. Maybe you've heard of it. And this expression right here says it's a probability of finding the electron within a certain space around the nucleus based upon its energy content. So location is proportional to energy of the electron. Location proportional to the energy of electron. You can only define the probability of finding the electron in a certain spherical volume relative to the nucleus, the distance from the nucleus and the energy content of the electron. And that's called the Heisenberg uncertainty principle. The position of the electron about the nucleus is defined in terms of statistical probability. We've already mentioned that. Of finding the electron within a specified region described by what we call wave function. So each electron has what is called a mathematical wave function that you plug into a fancy equation called the Schrodinger equation. And as a result, this Schrodinger equation gives what is called quantum numbers, and that's what we're about to focus on. The mathematics and development of these first postulates in here are way beyond the scope of the course mathematically. But the conclusions that came out of those postulates and calculations and mathematical analyses are within the scope of the course, and that's what I'm going to show you down here. The behavior of the electron about the nucleus of the atom is described by a set of 4 quantum numbers. That's what I was just mentioning. These numbers define the energy state of the electron, and it's called the Pauli exclusion principle. Very important here. Says that no 2 electrons have the same set of 4 quantum numbers. Now that's significant. I may have mentioned that back in the beginning of the course, but what it means is once you define those 4 quantum numbers, that is an energy window of the electron, and no other electron can occupy that window. And it's a proof that electrons don't run into one another. So that's the focal point of the rest of this lecture, is to begin showing you how to describe the electrons about the atom in terms of quantum numbers. So, but you are responsible for these postulates and how they relate to what we're working with now. A field of study. The electron behavior is applied to statistical mechanics. And statistical mechanics is just a study, a course, a discipline in probability and statistics. When the electron is applied to this mathematical field, this is translated or changed into quantum mechanics. Hence, that's where the foundation, oh, my bad. I'm sorry. The electron applied to statistical mechanics is all I'm trying to say is all of you've probably heard of quantum mechanics. Well, where did it come from? It came from a branch of mathematics known as probability and statistics, which is within the discipline of statistical mechanics. And that's just simply applying energy and of the electron to the mathematics that's in that chapter, so to speak. So that's the foundation that leads us into the next part. There are 4 quantum numbers. And I'm going to abbreviate quantum numbers QN because I'll be writing it so much. And to make it easy to remember, I've generated an acronym, POMS, pom-poms, like cheerleader pom-poms. P stands for principal quantum number. O stands for orbital quantum number. M stands for magnetic quantum numbers, and S stands for spin quantum numbers, COMS. Now each one of these describes something about the electron while it's orbiting in its orbit about the nucleus. The principal is the location of the electron in terms of ring, major energy levels. I'll just give ring because people relate to that a little bit easier, as in the concentric ring model. A principal quantum number of 1 means that electron's in the first ring about the nucleus. N equal 2, these have, I forgot to put in the symbol, N is the symbol for principal quantum number. If N equals 3, that electron that we're talking about is in the 3rd ring. Move it up here. Orbital quantum number is given by the symbol L and gives a shape of the orbital. On the handout that I gave you, last page, if you'll turn to the last page of that, you'll see some shapes. Now we'll talk about them as we go along. But those are orbital quantum numbers. Those are a result of what orbital? S orbitals are spheres, P orbitals are figure eights, D orbitals and F orbitals. Look like that. And they come out of the quantum mechanics. Magnetic is M and defines the orientation of the orbital. If you look at your diagram that I handed to you, S orbitals only have one orientation, but the P orbital can be oriented along the X, the Y, and the Z. That's what it means, orientation. D orbital, there are 5 orientations. F orbital, there are 7. And if we ever invent a G orbital, there'll be 9 orientations, but we hadn't gotten to there. Spin, of course, quantum number is M sub S, and is the rotation of the electron. Now, there's only 2 rotations, clockwise versus counterclockwise, and those are real easy. MS equals plus 1/2 is a clockwise rotation. And MS equals minus 1/2 is a counterclockwise. Rotation. So what I want to do now is show you where the numerical values come from and get these definitions in your head, and then we're going to stop in this section and jump over to how the quantum numbers are applied to the elements on the periodic chart to write out what we call electron configurations. Then at the end of that, I'm going to come back and show you how to pull the quantum numbers, the 4 quantum numbers for each electron. It works great, and students relate to this very quickly after you are able to write electron configuration. So just to review real quick, you see the definitions, the symbols, the symbology. This is the orientation set of numbers. We're looking to assign 4 numbers, but These are the orientations, and these would relate to that figure diagram that on the third page. We'll show you how to deal with it. And it talks about rotations, talks about shape numbers, talks about ring numbers, so forth, and how to assign the quantum numbers. And then it's got a thing down here at the bottom called the Aufbau principle. And that's where we'll start in putting together the electron configurations. So keep this page in front of you as we go through this. So the topic is electron configurations. Some people refer to this as the order of filling. I'll explain. Now, what order of filling means, if you have a collection of electrons, say over here, and here's a nucleus over here, and you're asked to take the first one and put it into an orbital around that nucleus. Where do you put it? Okay, that's what I'm talking about in terms of order of filling. So the order of filling is defined by what we call the Aufbau principle. And it's based upon arrangement of quantum numbers. Now here's what we're talking about. The first quantum number, what did I say? Principal, P-O-M-S, okay? So, and it has a symbol N. Now, the second thing is, how many rows do we have on the periodic chart? I've already mentioned it several times, 7. So what I want you to do is come down under the N, 1, 2, 3, 4, 5, 6, and 7. I'll go up here. Don't need all this right now. Aufbau principle, like that. What's the second quantum number? It's the orbital quantum number. And so what you come out here, and I'm just going to spring this out like that, and right in the middle of it, just put your L. That's your orbital symbol for your orbital quantum number. The third quantum number is the number of orientations. Okay? And what that refers to is how many orientations can a given ring hold? I'll say that again. Listen to me. How many orientations can a given ring hold? And if you look back at the diagram, the S can be, these are orientations. These are orientations of each of the orbital sets. Now, how does that apply to the Aufbau diagram? In the first ring, it can hold only one orientation. So I'm going to put a blank right there. The second ring, listen to me, holds two orientations. So put two blanks. Yes, you guessed it. Third orbital holds three orientations. And I'll explain what's significant here is the fourth ring, 4 orientations, and just keep going until you get through 7. 1, 2, 3, 4, 5. And then go 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, and 7. So these are the orientations. Now we're not going to get into spin just yet. So, but those are 3 quantum numbers that you have to apply into an electron configuration. What is the order of your S? You always fill with S orbitals first. I'm going to move the L up here. And then this second column right here is your P orbitals. Third column is your D orbitals. Here is your F orbitals. And G orbitals, if you ever invent any, and H orbitals. And on out here to the end is I orbitals. And you go in infinity, you know, and ring, you make theoretically. It's all mathematical anyway. Every one, in the first ring, we have an s orbital, and it's called a 1s orbital. You don't have any p orbitals because there's no room for a p orbital or d or any of the others. So one ring, one orientation, one orbital. The second one, we have two orbitals, an s and a p, because it's got two places for it. And these are referred to as the second ring orbitals. And then you go down here, and the s, p, and d are available. The d orbital shows up in the third ring. And it's the third orbital orientations, or third ring orbitals. Fourth ring will do 4 as you go on out. 4s, p, d, and that's where your f orbitals show up. In the fourth ring, you have those 4. In the fifth ring, you have 5 orbitals, 5s, 5p, 5d, 5f, and if we ever invent one, a 5g. Now I'm going to put a little line here because those haven't been invented, but theoretically, they're possible. And then 6 goes out to h. So S, P, D, F, G, H, and then this is S, P, D, F, G, H, and I. And these are 6 ring orbitals, 7th ring orbitals, if you ever get that high. Now, of course, we don't have that many. Actually, it breaks off. Let me get a card in here so you can see this. We have 4 and 5 have f orbitals. And this goes here. All of these that are to the right of the red staircase haven't been invented yet, but they evolved from the theoretical mathematical derivations of these. Now, the order of filling. Once you construct this, then it's called the diagonal method of filling. The first one you have to fill is the s orbital, so write a little diagonal like that through it. You can see this at the bottom of your handout, where I'm going, right here. And then once you fill the s orbital, the next one in line is the 2s orbital, and it'll point the arrow toward the next energy level. And then you come back up between those orbitals, and you go down through and point toward the 4th, like that. And you keep that going, and the blue lines and the direction of the blue lines define when you put things together, when you enter electrons, and where they would go if you had a stack of them. And that's, I'll stop there, because that's the largest one we have. So using the Aufbau diagram based on the quantum numbers, and I'll show you, you don't really need this. Once I get you oriented with the periodic table, you'll find out how to write out the configurations with little or no trouble at all. But this is where we start. Got to learn to crawl before we walk. The largest element that we can construct follows this. So where would we put the element X, biggie? 1s. And then what's the next orbital? 2s. And then 2p. See? We come back up here to the 2p, and then we go to the 3s. 3p, 4s. Then we come back up between the arrows, and we go to the 3d. Notice it drops down, starts putting electrons in here. Okay, and 3d, and then 4p, 5s, back up between the lines, 4d, 5p, 6s, and back between the arrows, 4f, 5d, 6p. Just keep going until we run out of blue arrows. 7s, back up to 5f, 6d, can't read my writing, 6d, and 7p. So as far as what we know, that's the biggest element on the periodic chart, bottom right, size big. Everybody good on following me so far? Okay, I'm going to make it easy for you in a few minutes, but this is how it evolves. Now, in the orbitals, they have a maximum number of electrons that you can put into given orbitals. I'll put that S, P, D, and F. S can hold 2, this can hold 6, this can hold 10, and that can hold 14 in a given orbital set. Okay? So as we write in, superscripts are used to indicate when they're full, or when an electron's in there. Electrons are put into that orbital. So this is 1s2, okay? 2s2, 2p6, see, 6 electrons. S's, we're back to S's and P's, so that's S2 and P6 max. Another S2, D. We hit 3D, we got to put 10 in there. We keep going now. I've got a point in all this. 6 for P, 2 for S, 10 for D, 6, 2, 14, 10, 6, 2, 14, 10, and 6. So everything's full at this point. Now, the object is not to write out this big dude here. Now, I think you understand that. The object is to write the basic electron configuration of a given element on the periodic chart. Okay? Now, to define the electron configuration, we're assuming neutral elements in what we're writing right now. We'll get to ions and gains, loss of electrons later on. What you do is you say the number of electrons equal the number of protons. Well, the protons, of course, is the atomic number. So if we wanted to write the electron configuration for carbon, it would be 6 protons and 6 electrons. Well, what we do is we go down this big list right here and go to 6 electrons and throw the rest of it away. 2, 4, and I need 2 in the 2p orbital. So carbon, colon, is the normal way to write this. It'd be 1s2, 2s2, and 2p2. So that's your electron configuration for carbon. If you wanted to write one for, say, nickel, here's nickel right here. It has 28 electrons. So we need to come down here to 28 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's a 3d8. Okay, so nickel is a 28, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then you drop back to 3d8. 8. There's your nickel. But you don't go all of this every time you need it. You can just figure out pretty much, and I'm going to show you in a minute, an even easier way to do all of this, like this. And there's one more for your benefit. How about bromide? Bromine is number 80. Right there. So I have, no, that's mass. 35. So we got 35 electrons to scribble out here. And that is Let me make sure. 4p5. Okay, so that'll be a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p5. I believe that's 35 if you add them up. 10, 16, 17, 18, 19, 20, 35. Right. Okay, so how am I doing it so quick? All right. Instead of using this, let's just use the periodic table. So what we want to do is figure out how to take the periodic table and write the electron configuration of any element on this chart. Well, first thing we need to do is understand what that blocks of elements apply to specific orbitals. That is, if you are in a given, if an element is in a given block, that means it's filling in that orbital, like this. If you're working with the group 1, group 2s, and the filling, the last orbital's filling, that's what I should have said. Everything in here is s orbital filling. Everything in there. So you can have 100 other stuff behind it called the core structure, but if you're filling in here, the last electrons in will be going into an s orbital. If you're working with the group of elements over here, everything over here is p orbital filling. And that block. If you're working in the transitions, everything in the transitions is d orbital filling. And if you're working in the inner transitions, those are f orbital fillings. So I could pick any one of them and work out to that element like this. We'll go back up and get something simple, okay? Let's start with nitrogen. Right here, okay. What do we see in nitrogen? It's in a p orbital filling. So everything before that position is full in the Aufbau diagram. So we'll start here and just put in as many as we need to get to nitrogen 7. So, and it will be a 1, 2, 3 electrons in that row. Look, 1, 2, 3. See, that would be a P3. If I was working with oxygen, the P would be a 4 electrons in the last one in, the last orbital. That'd be a P4 there. And F would be a P5. And then it would fill at the neon. It looks like this. So for nitrogen, we want to fill up the 1s orbital. Back here is full. Helium is full. That's the first energy level. Now we want to start filling in the second energy level. And we see we're outside of the s orbitals already, S2. So we're full. Now you get to 2p. 1, 2, 3. So there's your electron configuration. See how 2, 3. If I wanted to write it for oxygen, just to give you a contrast, for oxygen, it'd be a 1s2, 2s2, and 2p, 1, 2, 3, 4. And so you're full at that point. See, that's the position of the element in its row tells you how many, basically, electrons to put in that suborbital structure. How about, let's pick over here, calcium. Let's come over here to calcium. Now it's in row 4, so that'll be a 4s2 right there. We know at the end of it it's going to be a 4s2 because everything fills in here, and that's 4s1 potassium, 4s2 for calcium. And everything else behind it is already full. So you fill up the first row. First energy level is the first ring. It can only hold one orientation, maximum of 2 electrons. Now we'll fill up the second row, which is second energy level. It has 2 suborbital structures only, S and P. And so those have got to be filled because we're way down here in number 4 row. Same way with the third row. S2, P6, those are filled. But now I get into the row that contains my calcium. And it's in the second position of the s orbitals from left to right. So that's a 4, not 3, 4s2. There's your calcium.
Shouldn't it be 3p6?
Thank you.
3p6.
And that should be 2p6 also. So it's a matter of walking down through these rows and finding what the position is within a block that deals with that suborbital. Palladium. Okay? Palladium is 1, 2, 3, 4, 5th row, but it's 1, 2, 3, 4, 5, 6, 7, 8 elements into the d orbital. So that's going to be a d8 superscript. 1, 2, 3, 4, 5, 6, 7, 8. And we'll see how they shake out. Because see, you get to 4s2, the outbound diagram starts here with a 3d. This will be a 4d. This will be a 5d filling. See, it steps down 1. Look at your diagram I gave you originally on the outbound diagram. The flow chart will step down 1 when you hit there. It'll step down 2 when you get here. So here's where the inner transition. See, this is 58 right here, and I've covered it up. 57. So the inner transitions are here. And that. So if you got to 5d and had something here, it would drop down to a 4f. See, it just staggers down 1. Look at your flow. You don't worry about the outbound diagram. You just remember when you get to that position, if this is a 4s series, 4s right here, you got to step down when you get to the d orbital. But when you get back to the p orbitals, it steps back up to 4p's. It jumps back up to the next one.
So it would go from...
They're all consistent. Yes, ma'am?
So it would go from like magnesium down to...
Magnesium?
Or whatever the...
No,
over on
manganese, you mean?
In the left, on the s orbital.
Magnesium is in a 3s2.
So, but then it would go from there down...
No. You fill going across. Not that way. Everything in here is an s orbital.
You wrote 3D in the next section.
That's what I'm trying to figure out, is where you go from...
3p? You don't have any d's in here in the third row.
No, but you
wrote 3D.
You wrote
Whoa.
in there.
Well,
You wrote
let me
3D.
What?
You wrote 3D. And that's where
That's correct.
I'm trying to figure out where do you jump down, because you said something...
After the 4s1, 4s2.
Okay, so that row is 3D.
Yeah, see the first two?
Okay.
Everything in here is s. But you don't have any s's in, see, you have only s orbitals in row 1. You have an s and p's in row 2. Don't you?
No, that I
I know, wait a minute,
that.
just bear with
I'm
me.
trying to get it. Okay.
You have only SPs, and then you have 3 SP, and Ds will show up in the third row, but it starts there. You don't start a 3D here. You start a 3D after the 4S. Look at your diagram, the little flow chart thing.
Yeah.
What's the next one after 3P6? Let's see, yeah. What's that after 3P6? You go to 4S2, and then what's after 4S2?
3D.
That's where you start. All of the d orbitals are in the transitions. It's a pattern that you have to just get used to. You write electron configurations. I can do them all day long. You hold your periodic table. I don't have to scribble anymore. I'll show you. Okay, do titanium, Ti. Look at titanium on your periodic table. It's what, number 22. Okay? So what is the filling here? Well, I got to see this block in here? That's the transitions, right? What is the suborbital filling for the transitions? This is what? S. If your element of interest is in here, it's an s orbital. If the element of interest, well, this is also s over here, but if your element of interest is in here, what is it? Like if you're in antimony and tin and iodine, all of those are those elements fill up on their outer shell in the p orbitals. Everything in here is a p orbital. But everything in here, if your element of interest, say zirconium, vanadium, chrome, cobalt, any of those, you will be filling in the d orbitals. And of course, these are f orbitals down here at the bottom. Now, just pick an element in here. The order of filling goes like, we'll go back to titanium. That's one I was working on. Okay. Everything follows the sequence. Row 1 is 1s. Row 2 is 2s, 2p, because it's going to hold 2. This holds 1 orbital. This holds 2. This holds 3, 4, 5, 6, and 7 orbitals. Look on that last page on your handout. You'll see what we're filling with. Okay, so let's say we're still looking for titanium. That's in row 4. What's the filling order in row 4? Well, there's no d orbitals before that, so everything's s and p's. You see here? There's no d orbitals in that row. So you get to the end, you go here. At the 4th, you do have a 4th row s. But when you jump over that line right there into the d's, it steps down. Look on your alpha diagram. This one, this is a 3D right here. That's a 4s, 1 and 2. But this is a 3D. This one, uridium, is a 4D. And this one, lanthanum, is a 5D. And this one is a 6D. See how they step down? But these over here on this side of the line, that's a 4s, 4s. And then you step down. This one is the 5th row, 5s, 5s, and you 1 and 2. And then you step down to 4d. Is it making sense?
Yeah, I get it. I just don't. Why?
Huh? Why?
Yeah.
Look at your, that's the
No,
alpha
I
diagram.
get. Like I have the notes and
I
get
can't
everything.
calculate it for you. That's the point. That's not a
It
calculation,
was
dear
just
heart.
given to us that way.
I'm just giving you a shortcut for defining the order of filling. This is not a calculation. This is just,
No, I understand it. It just. I
don't
have a hard-
don't
I
let
have a
yourself
hard
stress
time
out over it.
With the why.
The y is the alpha diagram.
Okay.
The y I just stepped down, it follows the alpha diagram. If you need an answer to that, the y is steps down. Like this steps down. Look at your alpha diagram.
Yeah.
But I'm
No,
trying to
I
tell
get
you
that.
that that's a consistent trend. Once you pass the s orbital series, it always steps down 1. When you hit the d orbitals in the transitions, it goes back up. See, 4s, this goes back to 4p's. It steps back up. Look at your diagram.
Yep, cool.
When the rest of this, like,
Yes, sir.
Why is the diagram like that?
That's another story.
Yeah, that's
Oh,
what I'm
okay.
trying to figure out.
I already did that once. There. This is the diagram. It's like this. You have 4 quantum numbers. Okay? N, L, orientations, M, and M sub S. It doesn't have spin in here. That's where it comes from. The Aufbau principle says the electrons will enter the lowest available suborbital orientation. Lowest. And so this is the order of the lowest energies. So each one of these have an energy calculation that goes with them. And it's beyond the scope of the course. And so when you lay out all those energies, it gives you a picture like this. And so I jumped over the calculations and give you this and say, okay, if you need to define the electron configuration, follow the Aufbau principle and the Aufbau diagram. So then I went through it, and then down here I says, well, certain sections in the periodic table conform to certain filling parameters of the Aufbau diagram. So it's not a derivation where it comes from, in as much as it's already done and I'm applying it. And that's the order of filling. It's always in that order. I don't know any other way to put it. So if I were to pick lead,
So it's just that 4S is easier to fill than 3D, so it just goes to 4S.
no, I didn't say any easier to fill. I never said that. It's just the order. It depends on what element you're choosing. Choose an element, and I'll show you. I'll walk you through it.
I get how to write it down.
Huh?
I get how to write it down and.
Well, that's all you need. You don't need to understand its origin from the standpoint of where it's derived from, other than what is filling in this chart. D's, P's, S's, or F's. Now, if we picked, yes, sir.
Can you do 72 for me? Because I'm 72. out of
72?
Yeah, because I don't understand how you include the.
I'll be glad to if I can find it. Okay, 72 is tantalum, right here. Okay, what row is it in? 1, 2, 3, 4, 5. It's in the 6th row, right?
Oh, it's the one to the left of that, but yes, that's fine.
Oh, hafnium. I'm sorry.
I mean, it's.
I got it.
It's fine.
Give me a second. Let me do some house cleaning here, will you? Okay, question is number 72.